Electrochemistry is about using redox reactions to generate electrical current and about using electrical current to drive redox reactions forward. So that's what we're going to be doing with electrochemistry. All electrochemical processes involve the transfer of electrons from one substance to another, a redox reaction. So again, we use spontaneous redox reactions to generate current, and we use electrical current to drive non-spontaneous redox reactions. Said it twice. Redox reactions. So there's an oxidizing agent, something that's taking the electrons. There's a reducing agent, something losing the electrons, and we keep track of this using oxidation number. So I like this graphic, right? In order to keep track of what electrons are lost or gained, we assign oxidation states, right? So any metal atom going into a reaction has an oxidation state number of 0. All right, so we know that, right? It has all its electrons until it loses them and turns into zinc 2+. H+ ions in this case are taking electrons, become hydrogen gas. So we've seen this reaction before, right? Taking zinc metal and throwing it into hydrochloric acid. Chloride ions are spectators, they're not involved. It's about the H+ ions taking electrons to become hydrogen gas and forming zinc 2+. So we keep track of the whole thing using oxidation numbers. All right, so consider the redox reaction between copper 2+. Again, you take electrons away from something like copper, you make something hungry for electrons. So is this a spontaneous reaction or not, right? We'd have to look at, in the old days, I should say, we'd look at an activity chart to figure out whether this is going to happen. For this topic, we're going to be looking at standard reduction potentials to see whether this reaction is going to happen or not. But hey, in this reaction happens. Copper 2+ is going to take 2 electrons away from zinc. That's how we see this, and therefore it's reduced. That makes it the oxidizing agent. And zinc, with an oxidation state of 0, is going to lose 2 electrons, become zinc 2+. And in the process, it's oxidized, making it the reducing agent, right, causing the copper 2+ to be reduced. So it's just a review, stuff we already know about redox reactions. Oxidizing agent, reducing agent to make a redox reaction. They don't happen by themselves. Something has to give electrons, something has to lose. No, something has to give electrons, something has to gain electrons. That's what we want. All right, so in studying redox reactions, we can think of it in terms of 2 half reactions. We can think of it in terms of the zinc being oxidized, right, going from zinc to zinc 2+ by giving up 2 electrons. And we can think of the copper 2+ going to copper as a reducing half reaction. So if you take the oxidation half reaction, add it to the reducing half reaction, you get the overall reaction, right? Copper 2+ taking 2 electrons away from zinc. All right, this is going to be important for us for balancing redox equations. When we balanced earlier in the course, we picked redox reactions that were easy to balance. A lot of them aren't easy to balance. So there's a systematic way of balancing redox reactions that really makes it easier. Just following the steps. It's not a lot of thinking, man. It's just following the steps and you can balance your equation. If you don't have these steps, it's very hard to balance by inspection, just picking odd coefficients to shove in. It's called the half reaction method. All right, and in the half reaction method, we're going to be dividing up the equation into 2 half reactions, and we're going to go through a series of steps. I think 7 steps actually. So the first step is assign oxidation numbers to determine what's being oxidized, what's being reduced. All right, we know how to do that. And then write an oxidation half reaction and a reduction half reaction. And we get rid of spectator ions with this. Spectator ions just make it hard to balance. So omit the spectator ions. All right, step 3. We balance each half reaction, everything except for O and H in the half reaction. We're going to be balancing this as though it's in an acid environment. All right, so in this world, you're either in an acidic environment or a basic environment. And this is true of all redox reactions. They don't occur in neutral environments. They always affect the pH of the system. So if you're balancing in an acidic environment, we're going to balance the O's by adding waters to each side, and we're going to balance the H's by adding H pluses to each side. And we're going to add electrons to balance the charge. All right, so we'll show you how this is done. Step 4, we're going to multiply the half reactions by some whole number in order to balance electrons going in, electrons coming out. We're going to add the half reactions back together, canceling anything that's redundant, right, appearing on both sides of the equation. We're going to make sure it's balanced according to the number of atoms. We're going to make sure it's balanced according to the charge. So those are the 7 steps. So let's go through them. So here's an example, right? We've got permanganate reacting with iron 2 to form iron 3 and manganese 2 plus. All right, so this is happening in an acidic environment. All right, so again, this is an aqueous environment, and we're going to use the half reaction method to balance this. So first thing is split this up into 2 half reactions, right? So permanganate, going from a manganese of a, what is that, a +7 oxidation state to a +2, so it's acting like the oxidizing agent. And iron 2 going to iron 3 is acting as the reducing agent. All right, so iron 2 is the reducing agent, permanganate is the oxidizing agent. All right, so we've got our 2 half reactions. So we split it up now. Now we follow this step 3, which says balance everything except for O and H. All right, so 1 iron on one side, 1 iron on the other. That's balanced. 1 manganese, balanced. Now we're going to balance the O's by adding waters to each to the opposite side. And we're going to balance the H's by adding H pluses. So with the permanganate, if I add 4 waters to this side, I get 4 O's on one side, 4 O's on the other. Now I've introduced 8 H's on the product side, so I want to add 8 H pluses to the reactant side to balance the H's. So it's just following this step, right? Balance O's using waters, balance H's using H pluses. All right, now we're up to balancing the charge. We've got a +2 charge on the one side of the iron, a +3 on the other. So you're going to balance the charge by adding electrons. So if I add one electron to a +3 charge, it's now a +2 charge. So the charge is now balanced on each side of the half reaction. I've got permanganate with a -1 charge. I've got 8 H pluses, so it's +7 on this side, +2 on the other side. So if I add 5 electrons to this side, now it's +2 on the permanganate side and +2 on the manganese 2 side. So now the charge is balanced. All right, so we can't have 5 electrons going into the reaction and only 1 electron coming out. We have to balance that. So we multiply the top half reaction by 5 in order to get 5 electrons coming out of the reaction. And we don't do anything to the bottom half reaction. All right, so now we multiplied across by 5. Let's just make sure we got that step, right? Multiply everything across by 5. So 5 iron 2s, 5 iron 3s, plus 5 electrons coming out. And now I'm going to add the half reactions back together. So adding these together, canceling anything that's redundant. So the electrons are always redundant. So I cancel the 5 electrons. And that was it for this one, right? There was no anything extra to cancel. So I'm going to add these back together. Now we have it balanced in an acidic environment. So this is it. This is how you balance using the half reaction method, right? You follow the 7 steps and you check it over at the end to make sure that it's balanced. All right, so like I said, you're either in a basic environment and with a redox reaction or an acidic environment. So how do we deal with a basic environment? Well, it's going to involve hydroxide, right? That's a basic environment. So we follow the same steps as though we were in an acid environment. So we pretend like we're in an acid environment and we follow the 7 steps. And then at the end of the 7 steps, we add an 8th step. We're going to add hydroxides to both sides of the equation to get rid of any H plus in the equation and then cancel any redundant waters, right? When you add hydroxide to H plus, that's the same thing as water. So we're going to be making waters by adding hydroxides, and we're going to cancel the waters. Both sides. Eliminate the waters. All right, so here we go. So thiocyanide reacting with nitrate to make sulfur and nitrite. All right, so the 2 half reactions are thiocyanide turning into sulfur. Sulfur is going to a 0 state. Sulfur in thiocyanide has a -2 state. So it's being oxidized, and the nitrogen in nitrate is going from a +5 state to a +3 state. So those are our half reactions. So balance, so we follow the rules. Balance everything except for O and H, 1s, 1s, 1n, 1n. Balance the H's by adding H pluses. Balance the O's by adding waters and adding H pluses if we end up introducing H pluses. Balance the charge by adding electrons, right? So I have a -1 charge on the thiocyanide side, so I'd add 2 electrons to the other side, so I get a -1 on either side. +2 and -1 adds up to +1, so if I add 2 electrons to this side, that gets rid of those 2 positives, and now it's -1 on each side of the equation with nitrate and nitrite. All right, so 2 electrons going in, 2 electrons coming out. That means I don't have to multiply by some coefficient. I just got to add the 2 together, canceling anything that's redundant. So the 2 electrons cancel, one of the H pluses cancel, and now I add the half reactions together. And I end up with my balanced equation as though I were in an acid. Well, I wasn't in an acid. Thiocyanide a base. So the way I deal with this is add enough hydroxide to each side to get rid of any H+. So I've got 1 mole of H+ on the reactant side. So I add 1 mole of hydroxide to each side, the reactant side and the product side. OH- plus H+ is the same thing as water. And then I cancel any redundant waters that happen because of the hydroxide I add to get rid of the H+. And now I've balanced as though I'm in a base. So it's just following the steps. You get practice following the steps, and there's no, it's hard. It's easy. It's easier than doing it by inspection. It's easier than throwing in coefficients to try to balance. So balancing using the half reaction method.